All right, so problem number 2 on the exam will be a problem where you need to draw the forces, draw the free body diagram. Sum of the force equals mass times acceleration. This is just a particle, so we're not going to be summing the moments. We're just going to be drawing the free body diagram of a particle. Now, it might be XY free body diagram, but it might be normal tangential. So this one, I think we can see it's going to be normal tangential. I see some sort of spinning rotation. All right, so this is a tricky one. So look at this. Bowl-shaped device rotates about a vertical. This whole thing is rotating about this horizontal. It's rotating horizontally, right, about a vertical axis with a constant angular velocity, omega. If the 10 kilogram particle is observed to approach a steady state position when this theta is equal to 40, in the presence of a very small amount of friction, I think that kind of means negligible, right? Determine the angular velocity in rotations per minute of the bowl. The radius is 0.2. Okay, this is a tough one. I mean, I don't know about this one, but I do know there's some things we can fall back on. We can fall back on a free body diagram. We can draw a free body diagram and draw the forces, and only the forces. Don't make up any forces. But let's draw the forces acting on this particle, right? This object right here. So here's my ball M, my mass M. Before I forget, the weight, right? If it has mass, it has weight. 10 times 9.81 right here. What other real forces, what is touching this? I mean, there's no rope, there's no, it said very small, so no friction to worry about for this problem. But this bowl is definitely touching it right here. Do you want to draw this normal force right here or this normal force right here? Only draw normal forces when you have one thing touching another. I've seen way too many forces, free body diagrams and figures where someone might throw a normal force out there when there's nothing touching it. N is for things that are touching each other. If the ground is touching your block, if the incline is touching this, in this case, this bowl is touching the ball right here, so we have an N. I kind of like to draw it up here. Now, what angle is this? This is 40 degrees right here. Let me kind of look. This would be 40 degrees right there. Okay, and that's it. I mean, it's a pretty simple free body diagram. I think this problem is going to turn out to be a lot simpler than it seems, but we've got to get the free body diagram correct. All right, now, axes. We've got to define our axes. Define the axes according to the acceleration. Now, this one, I think you can kind of see as a spin is a normal tangential problem. But what direction is normal? What direction is tangential? Normal direction is always into the curve. Okay, but be careful. I mean, I see a curve right here, but that's not the curve. It's into the curve of the path. Visualize the path. Visualize the path. And I think for the final exam, you'll have time to really read this and be careful and think about what it's going. This whole thing is spinning horizontally around here. All right. It's not. This ball is not going like around here in a circle. It approaches this steady. It's kind of sticks right here and moves with this disc. So the normal direction would be into the curve right here. That would be my normal direction. That is perfectly fine if the normal force is not in the normal direction. Normal direction is into the path, into the curve of the path. Visualize the path, draw an arrow into the curve. All right, tangential would be into the page, and then I'll call this other direction Z or Y or something like that. So there we go. So I mean, that was really simplified, but don't overcomplicate it. But it's important to get that free body diagram correct. I think the most important part of the problem. is getting your free body diagram correct. Getting a good free body diagram with the good forces and the correct axes. All right, then you're ready to sum the forces. And so, you know, I think it's obvious when you've got normal and tangential and normal and z axes, you're summing the forces normal direction equals MA normal. Summing the forces tangential. If we were tangential, this one we're not worried about tangential, and we'll sum the force in the other direction. All right, sum the force in normal direction. Let's see, in the normal direction, in sine 40, I think that's it, equals M, right, MA normal. What is A normal? A normal is V squared over R, or R omega squared. So this is M, R. Let me come back to R. Actually, I think we can do R. R is what? R is not just 0.2. Okay, this R right here is the distance that my point is away from the center of rotation. Where is the center of rotation? Right here. So this is what I'm looking for in my R omega squared equation. So what is that length right here from there to there? Well, it would be 0.2 from there to there. And what would this be if this is 40 and this is 0.2? 0.2 sine 40? Yeah, so I've got my R to be 0.2 plus 0.2 sine 40, whatever the value that is, 0.3285, something. All right, and I don't know omega because I'm trying to find the angular velocity in RPM. First, I'm going to find omega in radians per second, and then I will convert radians per second to that angular velocity in RPM. All right, so I think that's my equation. I don't know n just yet. I don't know my angular velocity omega just yet. Okay, well, let me jump over to my other equation. Let's jump over to another equation. In cosine 40 in the positive z minus 10, 9.81 in the negative z equals MAZ. Is it accelerating in the z direction? No, it reaches this steady position. It's not getting higher or lower in the z direction, so that would be equal to 0. Okay, so N is going to be 128 newtons. Plug that in up there, yes. All right, and then I'll get omega is 5. Make sure I've got this right. 5.01. All right, radians per second. Now, my omega is always going to be in radians per second. If we're doing R omega squared right here, I really could keep up with my units a lot better, but that's radians per second right here. All right, so that's my answer. If I could stop right there, I would have. But that's my the omega is 5.01 radians per second, but it wants the angular velocity in RPM, in revolutions per minute. So it's just a unit conversion. 5.01. What are the units I have here to begin with? Radians per second. Now I want to convert radians per second. Sorry, I like to do it this way. Radians over seconds. I want to convert radians to revolution. I know that 1 revolution is 2 pi radians. And I want to convert seconds to minutes. I know that 60 seconds in 1 minute. So there we go. R per minute. I have 47.8 RPM. 47.8 RPM. So that's how we answered that question. Let's take a step back and look at what we did. Free body diagram, define our axes, sum the forces in one direction equals MA in that direction. And for normal acceleration, you can do either V squared over R or R omega squared. I chose to do R. It was a tough R, but R omega squared. And then sum of the forces in the other direction equals MA in that direction. And then solve for the unknowns and really answer the question that it's asking you.